and we will look at this. I have sent a bunch of stuff about the final exam in an email. If you have questions on your final grade, like or where you're sitting at in the course, I'm getting lots of emails right now. And this is just the time of the semester that those emails roll in. So if I'm behind on my emails, it's because I do have lots of them daily. But it's not an excuse. I'm going to get back to you. Just thank you for being patient with me, really, is all I'm trying to say. It may not be the exact day of, but hopefully by the next day, maybe at the latest 2 days, I will get back to you. But I will return your emails ASAP. Okay, share screen. Come on. There it goes. Okay, here's exam 4 on paper version. You guys have probably forgotten what paper exams look like, haven't you? Here's what it would look like if you were taking it in person. We're going to scroll down to the last multiple choice here and turn it this way. So when I taught you guys osmosis, we talked about it was the movement of solvent particles through a semi-permeable membrane from an area of high concentration to low concentration. And what I was talking about on the video is the concentration of solute particles. Okay, if you have, I don't know, a cell, okay, and imagine inside the cell, like a red blood cell, you have a lot of different solutes, different ions or things like that. And outside of the cell, you have a low concentration. Solvent will move from an area of low concentration to high. So when you read question 14, if you look at the key, it says that, let me turn my pencil on. It says that E is the right answer. Both B and C are correct, but let's I actually had to change this. Okay. Now, if you put E, email me, because I'm still going to give people credit for that, because the way I meant to write one of these answer choices just did not come across the way I was intending. There's some ambiguity within it. And that is answer choice B. Osmosis is the passage of solvent particles from an area of high concentration to area of low concentration. I did not specify if I was talking about solvent or solute. And I realized that, okay? In the video, I taught it as though we were talking about solute concentration. So that is the way I'm going to assume you guys interpreted it, because that's the way I taught it. In my head, I think I was trying to say high solvent concentration to low solvent concentration, but that's just not how it, you can't interpret that from this question. So this is actually not true, okay? And so because that's not true, E is not the correct answer. So C, osmosis occurs to a difference in solute concentration, which creates a gradient. That is true. So if you pick C, I've already corrected it on Blackboard, and you probably got points for that. A lot of people I saw miss this one, and I think they put C. But if you put E on that, then I will give you points, but you have to email me, and I'm going to go check. If you put A or B or D by itself, then I'm not giving you points for it. Okay. Anyways, I just wanted to correct that. That's probably 3 points back if you've had your exam graded and noticed that it changed slightly. Next question, somebody asked if we could look at this one. One on Ka values. So based on the Ka values for the following weak acids. So we have an assortment of weak acids here. I said rank the solutions in order of decreasing pH. So start with the solution, the weakest of the weak acids, and then you're going to end with the strongest weak acid, okay? How do we do this? We're looking at their Ka values. Ka, a few things to remind you about Ka. Larger Ka equals stronger acid, okay? Stronger weak acid. So the larger Ka that you have, the more dissociation that occurs, and the stronger your weak acid is. The stronger the weak acid is, the higher the concentration of H+, and the lower pH. So the one with the largest Ka should be listed last. The one with the smallest Ka should be listed first in this problem, because the smallest Ka, let me pull the chat up. The one with the smallest Ka will have the highest pH. And if you have other questions about the exam, other problems you want me to look at, I'm getting something in the chat, email me and we can set up a separate Zoom. I just can't take up all the lecture time today. We have to get on this review. So if you have other questions about the exam, I'm happy to walk through. In fact, you can see all this work. I literally just this afternoon walked through these three problems with another student. So I'm happy to do this with you. If you want to look at the exam, anything on it. Let's finish this problem though. So what that means, we've got to look at the exponents here. The exponents are going to tell us which one's the largest and which one's the smallest, okay? The smallest, 10 to the negative 10. This is the smallest, Ka. So this is the weakest acid, which means it will have the highest pH. Okay, so this one, because we're doing decreasing, meaning one with the highest pH is number 1. This one is number 1, all right? Then as you go down, the next smallest would be 10 to the negative 8. So this would be number 2. Next smallest is 10 to the negative 7. This one's number 3. Next smallest is negative 5. This would be number 4, and then number 5. So this one would have the lowest pH because it is the strongest of the weak acids. Okay, so that's how that one should have been done. Any other questions, shoot me an email, we'll set up a Zoom, whatever. Or I can respond via email too. Okay, let's jump over to the review. Here we go. We're going to get into this. I put one more hiking trail in. Are you surprised? Squeezed it in. And how appropriate that it is named the Goat Trail, the greatest of all trails. Actually, it's not my most favorite, but it is a beautiful one. The Goat Trail, you hike through some forest. It's in the Buffalo River, Ponca area, and you have this beautiful overview of the Buffalo River down here. And if you float the Still Creek Kyle's Landing portion of the river, you will pass the Goat Trail up on the cliff, that is. And anyways, this picture, you can't really see the trail so much as the view from the trail. It is just on the edge of this whole, you can see this whole cliff edge here. It's just one big sheer cliff, and you're just hiking along the edge of it. So I would not recommend taking small children or animals on this hike. I would just take adults only. Here's another view from it. This is kind of the trail over here that you can see. There's no rails, there's no nothing. So it's a lot of fun though. It's really pretty. Yeah, I like it. So all that to say, because this is our last time together, unless you join me tomorrow, if you go hiking over the break, if you get out and do any or hiking in through the spring, shoot me an email. I would love to hear. I'm always looking for new trails. If you go on a fun one that you really enjoyed, let me know about it. Okay, chapter 1. We're going to get through chapters about 1 through 4 today. If I am just flying way too fast, please let me know. I need feedback from y'all. I can tend to try to move through this stuff, but this is going to be kind of like, anybody ever read the Cliff Notes back in high school? You didn't make time to read the book like you're supposed to. So you read the Cliff Notes, which is always a lifesaver. This is going to be kind of the Cliff Notes edition of these things. It's just the main summary. Okay, so we're going to hit the high points. I'm not saying these slides only are what you should study for the exam. Here's what I recommend studying for the final exam. Exam keys. Go back and look at how things should have been worked or rework exam problems. And then quizzes. I'm going to make sure all the quizzes are opened up so you can go back and look at any of the quizzes. And homework problems from Mastering Chemistry or the textbook problems I recommend. Now, I understand there's like 100 problems, okay? That's like a lot of problems. Don't spend your time working hundreds of problems. You don't have time to do that, okay? Nobody has time to do that. Just pick a few from each chapter and work a few. And anyways, hopefully that will help kind of guide you as you have limited time, I know, to prepare for finals because you have other finals, but for this course. All right, let's get into it. Chapter 1, we talked about how to classify matter. And what we looked at is we said, basically we asked the question, does it have a uniform or a varied composition? If it had a uniform composition, then that was a pure substance. Pure substance has a uniform composition. I'm going to write comp. So what is a pure substance? An example would be either an element or a compound. All right. If it did not have a uniform composition, if it was varied. Oh, question in the chat. Is this recorded so we can watch again later? Yes, it is recording. Okay. And I will post that recording. All right. If it had a varied composition, then it was a mixture. And this is varied. And remember, there's two kinds of mixtures. Anybody remember the two kinds of mixtures? Two kinds of mixtures.
Isn't it homozygous?
Half the word. Homogeneous or homogeneous.
My mind blanked on the other half. I'm sorry.
You're good. Yeah, homogeneous and heterogeneous, or homogeneous, heterogeneous, any way you want to say it. Those are the two kinds of mixtures. And so this is hetero or homogeneous. All right, homogeneous would be like vanilla ice cream. Okay, heterogeneous would be like spaghetti. I don't know, something where it's not evenly distributed throughout. Okay, or like the vegetable soup, or throw some Oreos in your ice cream. Okay, the 4 signs of a chemical change. So we talked about how to class. So if I gave you a multiple choice and I was like, here's a substance, is it a compound? Is it a homogeneous mixture or heterogeneous? Hopefully you can classify it. 4 signs of a chemical change. We're just going to write those out. We looked at the difference between chemical and physical changes. Remember, physical changes were changes between solids, liquids, and gases. Okay, that's physical changes. Melting, freezing, evaporating. But chemical change happens if you get one of these 4 signs: a temperature change, color change, if you form a precipitate, or if you get gas bubbles. All right. Any of those things indicate for sure a chemical change. So questions I would ask are like, is roasting a marshmallow a chemical or physical change? Is burning a candle a chemical or physical change? Is a pond water, rainwater evaporating off the ground physical or chemical? Things like that. Okay. Prefixes are a next big topic that we went over in chapter 1. So the 4 I wanted you to know were kilo, centi, milli, and micro. We're going to write out how these are related to the base unit. Hopefully this is just like comes pretty naturally to you guys now, because we've done this all semester long. So let's write this out for a second though. Kilo is the one that's bigger. And when I say base unit, what do I mean? What comes to mind when I say the word base unit? What are examples of base units? The gram, it'd be one. Yes, thank you, Zoe. Gram, liters, meters. Okay. So remember that 1 kilo equals 1,000 base units. I'm going to abbreviate base unit. Okay, next was centi. Centi is smaller. There's 100 centi, whatever, centigrams, meters, liters, in 1 base unit, be it a gram, meter, or liter. Milli, there was 1,000 of these. And then gram, meter, or liter in 1 base unit. There's 1,000,000. When I said centi, my Siri came on. I don't need you, Siri. 10 to the 6, 1,000,000 micro. Oh, I wrote the symbol, not the micro. Gram, meters, or liters in 1 base unit. Okay, so all these 3 are smaller than the base unit. Kilo is larger. Okay, so these are the 4 that I really wanted you to just kind of know very quickly. We're going to do a couple practice problems with these in a second. The next big thing from chapter 1 were temperature conversions. So I will give you the equations for Fahrenheit to Celsius and Celsius to Fahrenheit. Those were on your exam 1 resources page anyways. Any equations that were on resources page from any exams you'll have on a collective resources page. But remember, if you need to convert from degrees Celsius to Kelvin, that you take your degree Celsius temp and you add 273.15. Don't forget the 0.15. You know who you are if you've done that. Okay, density. Density is important. It is mass over volume. Now, we measure density different ways because we have different kinds of substances. For liquids, the units that we use are grams per milliliter because liters are just a very easy way to measure liquids. It's a volumetric unit. But if we have a solid, remember, we can measure density with gram per cubic centimeter. And what's the relationship between a milliliter and a cubic centimeter? Anybody remember? One milliliter is 1 cubic centimeter. Okay. So that should not mess with you if you have milliliters or cubic centimeters. They're the same. Now remember, we did a whole dry lab. The very first dry lab we did was the second lab of the semester on conversions, density, little word problems that were kind of like complex conversions, and specific heat. Now, I will tell you, specific heat is not going to make it on the final exam. I actually put a note on that down here. Okay, Merry Christmas. That's my Christmas gift to you. No specific heat. So I'm trying to mention things here and there that I know aren't on there so that you really can focus on just kind of narrow down what you're spending your time studying in some small ways. All that to say, that dry lab, I recommend going back and just reworking those problems to remind yourself the density and conversion stuff. All right, speaking of conversions, let's work out these two following conversions. Micrometers to millimeters and kilograms to centigrams. We're going to do them in one step, okay? So we need the relationship between micrometers and millimeters, right? Well, I'm going to relate both of them to a meter. There are 10 to the 6th micro, that's the symbol for micro, meters in 1 meter, right? And then millimeters, there's 1,000 millimeters in 1 meter. Now, because these both equal 1 meter, guess what? They're equal to each other, okay? These two terms, we can make a relationship. A million micrometers equals 1,000 millimeters. So I'm going to plug those numbers in. Here's what I'm going to do. In one step, we're going to start with the number given, 14.4 micrometers. Now, I'm just going to I want to cancel micrometers. So a million of those on the bottom equals 1,000 millimeters because both of those equal a meter. And so you can just save a step, do it in one swoop. And you should essentially divide by 1,000. So you get 0.0144 micrometers. Okay. Okay, what about kilograms and centigrams? So let's relate both of these to the gram. Well, I'm going to relate both of them to 1 gram so that I know they're equal so that I can relate the two numbers to each other. How many kilograms is in 1 gram? 0.001 or 10 to the minus 3. Usually I don't write it like this. Usually I write it with whole numbers or I don't write decimals. But some people do it this style and it's okay. 0.001 kilograms equals 1 gram, and then 100 centigrams equals 1 gram. So now because these both equal a gram, these numbers are equal to each other. We can start with 1.35 kg. So 0.001 kg equals 100 centigrams. We're going to cancel out kilograms. So 1.35 times 100 and then essentially times 1,000. You should get 135,000. So what you got? Oh, also I see the chat. Angelina, thank you. This up here is the wrong unit. I canceled out micrometers, so this should have been millimeters. Sorry for any confusion. Okay, questions on that? Good. All right. Also, how many of you have like moved back home and just stayed at home? Somebody sent me an email that during exam 4, they like their computer like pretty much almost died on them and their dog threw up on the carpet while they were taking exam 4. And I was like, that's life at home, isn't it? If you try to get anything done. So, all right, we're going to work a word problem now. And this is 1.76 from the textbook. You might even recognize it. It's just a good little kind of remind yourself how to work word problems like this. So the normal value for blood cholesterol is 200 milligrams per DL. What is DL? It is deciliter. There are 10 my powder because I locked her out of my room during the exam. Ha. Yeah, welcome to life at home. It's a little more distracting. Equals 1 liter. All right, if a normal human adult has a total blood volume of 5 liters, how much total cholesterol is present? So try to work this. Where do we start? You need to write out your relationships. And we're trying to get how much total cholesterol. It doesn't actually tell you what units to use. So we're just going to use units of milligram because that's what the problem gives us for units of cholesterol, milligram. So we don't have to change that. So we have this relationship, 200 milligrams of cholesterol per deciliter of blood. We have this relationship that 10 deciliters is equal to 1 liter. And then we have this relationship that 5 liters for 1 adult. So we're just going to start with this first one. Per 1 deciliter. Now, I want units of milligrams in my answer because it was just how much cholesterol. So we want to keep that unit because that is the unit that belongs to cholesterol, milligrams. But I want to cancel deciliters. I don't want to know how many milligrams per deciliter. I want to know how many milligrams of cholesterol per adult. So I'm going to cancel deciliters by plugging in the second relationship, 10 deciliters for 1 liter. And then I also want to cancel liters. So I'm going to use my third relationship down here. Plug in for every 5 liters for every 1 adult. 5 liters of blood for every 1 adult. Okay, liters cancel. Okay, now we'll end up with milligrams per 1 adult. So 200 times 10, 2,000 times 5 is 10,000 milligrams per adult. And that's milligrams of cholesterol. Okay, remember, specific key, it's not going to be in the final, so we haven't spent any time going over it. All right, that's kind of it for as a summary of chapter 1. And we're going to talk about chapter 2 now. So the first thing we hit on in chapter 2 was Dalton's atomic theory. And surprise, surprise, I just put it on the next slide so we can refresh ourselves on the 4 parts of Dalton's atomic theory. First part says that all matter is made up of tiny particles called atoms. Number 2, atoms of a given element. All elements are different. How are they different? Well, they're different because they weigh different things. So they differ from atoms of all of other elements. I should have written by their mass. Okay, because they have different number of protons and neutrons and things like that. Part number 3, it's compounds. Consist of atoms in specific ratios. Only whole atoms can combine into compounds. So here's what that means. You cannot have H 3 halves O, right? You can't have half an atom. It's only whole numbers as subscripts. It could be H2O, H3O plus, but it can't have half an atom. All right, whole numbers on the subscripts when we write chemical formulas. Number 4, chemical reactions only change the way atoms are arranged. They do not change the type of atom. Okay, essentially this is kind of hitting on a law that says matter is not created or destroyed. Law of conservation of matter. We don't create new atoms when we do a chemical reaction. We just break bonds and rearrange them. All right. So that's Dalton's atomic theory. Atoms, subatomic particles. So we did that one. Next, let's talk about the subatomic particles. What are the 3 subatomic particles? Do y'all remember? I want you to know their charges. Proton, question mark? Oh, come on. By now you should be like, proton!
Neutron and electron.
There we go. Anybody remember the video we watched about oh, what were the gang names? I forgot. The New Boys, I don't remember. Protons. Okay, they have a plus charge. And where are they found? Okay, their arrangement in the atom. Where are they in the atom? They are in the nucleus. And what is their role in the atom? I'm actually going to erase that. Their role in the atom is they contribute to the mass. They weigh something, 1 AMU. They also identify atoms. Okay. We identify carbon is carbon because it has, I think it's 6 electrons, or sorry, protons, 6 protons. Hydrogen is hydrogen because it's 1 proton. So if you change the number of protons in the atom, you change the element you're talking about. All right, neutrons is the second one. They have no charge. They are also in the nucleus. And what is their role? They contribute to the mass of the atom. They also weigh 1 AMU. Protons and neutrons weigh the same. And they are how we get isotopes, okay? So they're important because we vary the number of neutrons in an atom and we can get isotopes. So I'm just going to write isotopes here. We'll define what an isotope is in a second. So 3 electrons. Remember, we abbreviate these E minus. They have a negative charge. They are not in the nucleus. They are in the electron cloud, which surrounds the nucleus. Remember, if we draw a picture of an atom, there's the nucleus, and there is the electron cloud, okay, around it. And electrons are out here. What is their role? They are responsible for the chemistry of atoms. Excuse me for just a second. All right. So remember those things. And now let's talk about isotopes. What is an isotope, first off? How do we define that? It's basically atoms with a varying number of neutrons. That's what an isotope is. So carbon-12 has 6 neutrons, carbon-13 has 7 neutrons, but they're both still carbon because they both have the same number of protons. So a great example of a style of question I could ask on the final exam about isotopes. If you're looking, this is 2.42 from your textbook. If you're looking at these A, B, C, and D, we're going to go through and give the number of protons, neutrons, and electrons in each of these isotopes. Okay. Now, a couple things you may need to remember, mass number and atomic number. Okay. The mass number, what is that? I'm actually going to write that down here. Mass number. It's abbreviated with an A. It's very confusing, but it is the number of protons plus the number of neutrons. The number of protons plus the number of neutrons together, because those things contribute to the mass of an atom. And atomic number is just the number of protons that we identify an atom with, just the number of protons in the nucleus. Now, when we say an isotope, when we write it or say it, we indicate the isotope with the mass number. Okay, so for example, if you're looking at A here, what is Al27? Well, Al is the symbol of the element, but what is 27? I'm telling you here, 27 is the mass number. That's how we talk about isotopes. So that is the number of protons and neutrons. So if we're going to look at how many protons and neutrons and electrons there are, well, one, it would be helpful to have a periodic table here. I actually didn't have one this morning. It was very inconvenient. So I put one on here. Here's aluminum. Wow. That is so blurry. I can't even make the numbers out. Okay, if you have a periodic table handy, or maybe Google one real quick, take a second, pull up a periodic table, because this did not go how it was planned. It's number 13. I don't know if you can tell. This is awful. That's supposed to be a 13, all right? So you will look at a periodic table. You'll get the atomic number. It's the one at the top. So that is the number of protons. So there are 13 protons in aluminum. And we know in any neutral atom, the number of electrons is identical to the number of protons, always. Now, when we get to cations and anions, that's different. But for now, we're talking about neutral atoms, so we have 13 electrons as well. But how many neutrons do we have? 13 protons, 13 electrons. How many neutrons? Well, we will take the mass number, we'll plug in the number of protons, and we'll solve for the number of neutrons. So we're just going to do the mass number minus 13 here, which is 27 minus 13. We have 14 neutrons. That is how you solve a problem like this. Okay, next, B. We have the element symbol. You can always go to the periodic table because you'll always have the symbol, and you can find the number of protons and electrons from that. But it gives you two numbers. The top one is larger, and this is always the top one will always be the mass number. The bottom one will always be the atomic number. Okay. So because 14 is the atomic number, that's the number of protons. And that's also the number of electrons. And to get the number of neutrons, we just do 28, the mass number minus the atomic number. And that gives us 14. That's how many neutrons there are. Okay, so C is similar to A. We have B, 11. 11 here is the mass number. When you see it like this, if you see a single number, they're communicating the mass number. So we need to go get the atomic number from the periodic table. Mine is blurry, but maybe you can tell that's a 5 on boron. If you have a periodic table, you can probably see it more clearly. So we have 5 protons and 5 electrons. And then we'll do 11 minus 5 gives us 6 neutrons for boron 11. Okay, lastly, silver, 47 is given. That's the bottom number, it's the atomic number. So that's the number of protons and electrons. Then we'll do 115 is the mass number minus the atomic number. And that gives us 68 neutrons. Okay. That's isotopes. Now, also, why are isotopes important? We talked about 2 reasons isotopes are really actually valuable to us. What just happened? Right here. 1, energy. We use isotopes in nuclear reactors, okay? The big like smokestacks you'll sometimes see driving by interstates, different cities have them. We extract energy, enough energy to power whole cities and beyond sometimes. 3, I told you my brain is not here today. 2, medicine, okay? I use the example of iodine 131, okay? If you know people that have had thyroid issues before or thyroid cancer, they'll give them radioactive iodine 131. It's an isotope of iodine, and it's a radioactive isotope, so it'll go in, be absorbed to the thyroid, and the radioactivity of those isotopes will kill any cancerous cells. So that's 2 reasons they're important. I want you to know those things moving on from this course. All right. Also, we talked about how when you look at a periodic table, there is similarity in the arrangement among groups. What is a group? A group is a vertical portion of the periodic table and chemical behavior, okay? So elements that are in the same vertical group, they share similar chemical behavior. So going back to the periodic table, again, I know it's blurry, but for example, the halogens over here, I'm going to put a box in around the halogens. If I said fluorine is a toxic colored gas that reacts violently with group 1 elements, blah, 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 what element would you expect to be similar to fluorine? And I listed a bunch of different elements. You would only expect elements in the same group to be similar to fluorine, okay? Remember we watched the videos on how different metals explode with water? They kind of react explosively with water. That's because those are group 1 metals. Well, it's hard to see in the red, but these over here. So remember that. We looked at how the periodic table is arranged and how elements in the same group share similar chemical behavior. Also, we looked at the periodic table and we learned how to count valence electrons from this. Do you guys remember how to count valence electrons? Please say yes. Okay. So you count them according to main groups. So what are the main groups? Right here. This is main group 1. This is main group 2. You skip the transition metals. Come over here, boron. This is main group 3, 4, 5, 6, 7, and 8. The number of valence electrons that any element has matches its main group numbering. So any element in main group 3 has 3 valence electrons, and so on and so forth, okay? That is critical. Let's go back to here. I think problem 2.74 just kind of lists different elements and says, you know, how many valence electrons are there and write out the electron dot symbol. Do you guys remember how to write electron dot symbols? You put 1 electron on each side if it has 4 or more, and then you can double them up on another side once each side gets 1 electron. Anyways, I think problem 2.74 just has you write out stuff like that. But understanding valence electrons is key for everything in chapter 3, which is what, and 4. Okay, which is what we're about to get into. So ions and ionic compounds. So do you guys remember ionic bonds? What are these? They are the basis for how we get ionic compounds. And an ionic bond is when an electron is given or received I'll just say between atoms. Okay, it is completely given or received, not shared. And it's not just any electron, by the way. I should have written this in. It is only valence electrons that can be given or received. And I forgot to write this earlier, but remember, if you have multiple energy layers around your nucleus, which one is a valence electron? They're the ones on the outermost energy shell. So they're not on the inner shells. They are on the outermost shell. Those are valence electrons. Those are the ones can be given or received, traded, essentially. Once this happens, you end up with ions. So we have 2 kinds of ions. Anybody remember the 2 kinds of ions you can create?
cation and anion.
Yep. Cations and anions. Okay, so cations, do they give or receive electrons? Anybody remember? They give away.
We can't see what you're typing or writing.
Oh man, I might need to reconnect it. Stop share, reshare. Can you see that now? Okay. Cations give away electrons. Oops. And when they do, there's now an imbalance between the number of protons and electrons. So for example, if you have, well, we'll go with aluminum because we looked at that earlier. Aluminum we saw had 13 protons and 13 electrons, right? But if it gives away an electron, in fact, it gives away 3. So if it gives away 3, so -3 in this column, now we have 10, but we don't change the number of protons. We still have 13 protons. And because they carry plus charges and electrons carry negative charges, when you add these two up, you get +3. Okay, that's how the imbalance between electrons and protons gives us the overall charge on the cation. Or we could vice versa do it for anions, which receive electrons. And these have cations have a positive charge overall, and anions have a negative charge overall. Okay. Now, here's where, if you kind of didn't grasp some of this stuff, you might have struggled throughout the semester, because all of this we summarize with the octet rule. The octet rule helps us predict what kind of charge each atom will carry as an ion. And here's the octet rule. It's the tendency of atoms to gain or lose electrons to achieve an octet. They want 8 valence electrons in their outer shell. There's something very stable about that. And that is a completely filled shell. So based on how many they need to give away or receive to get that outer shell is how you predict the charges on cations and anions. Okay. All right. That's all I'm going to say about ions for now. But let's talk about how to name them and write ionic compounds. Okay. Naming ions. The rules for that, we had rules for naming cations. And they were different depending on if you're a main group cation or if you're a transition metal cation. Let's go back to the periodic table for a second. Main group cations are in 1, 2 right here, and 3. These elements right here and these groups are your main group cations. Anything that is in this, anything in this square right here, I really don't know if you can see that. Those are transition metals, and we have different rules for naming those. So cations, if you are a main group cation, you simply write the element name, and then you add the word ion, plus ion. So for example, if you have potassium, that's a main group, you would just write potassium ion, okay? Okay, plus you would call that potassium ion. However, if you are a transition metal, cation, you write the element name and then you put Roman numerals in parentheses. And then you add the word ion. Okay, why do we do this? This is because transition metals can carry more than one charge, remember? So you can have, chromium can be a +2 or a +3. Lots of different transition metals can carry different charges. So anyways, so if we did have the chromium 2 ion, Cr +2, we would write it chromium 2 ion, all right? Or if we were writing it into a compound, you would have to include the Roman numerals. Anions, you simply name the element and you change the ending to IDE. Okay, and then you put the word ion. So fluorine is F-. We call that the fluoride, IDE, fluoride ion. Sulfur would be the sulfide ion. Chlorine would be the chloride. Oxygen, oxide ion, okay? I think you get it. All right, now we're going to practice naming these. Go ahead and look at these 3 compounds, whether I've written it out or given you the formula, and try to do the opposite thing. So the first one, I've given you the formula, so you try to write the name of the compound. And the second one, I gave you the name, you try to write the formula. Remember, overall, these have to be neutral. So for like the second one, magnesium phosphate, you have to consider the charges on your cation and anion and how many of each one you need to get a neutral compound overall. The amount of positive charge has to add up to equal the amount of negative charge. And you don't put the word ion into the compound because it's not an ion, it's a compound now. All right, let's look at the first one. Calcium nitrate. So we'll just write, well, I just said it. Calcium. And we don't have to put 2+, right? Because calcium is a main group. So it should be calcium. And then NO3, I put your polyatomics down here, by the way. NO3 is nitrate. So it would just be calcium. You don't write calcium ion, nitrate ion, just calcium nitrate. All right, magnesium phosphate. What charge does magnesium carry?
Is it 2? I don't have a periodic table. Is it 2+?
Yeah, 2+. And you know that it's a plus because we always write the cation first, remember? Cation goes first, anion goes second. So magnesium is a 2+. What is phosphate? Well, let's just go to our table down here. Phosphate is PO4, 3-. -3. So how many of each do we need? We have Mg 2+. We have PO4 3-. Remember the switch trick? The value of the charge on the cation is the number of anions that you need. And then the value of the charge on the anion is the number of cations that you need. So you should get Mg3PO4, and then if we need to put parentheses, if it's a polyatomic and you have more than one, you put parentheses around it, and you put how many you need as a subscript outside, so 2. And then let's double check that we have a neutral compound overall. We have 3 cations, and each one is a +2 charge, so that adds up to +6. We have 2 anions, and each one is a -3 charge, so that adds up to -6, and then that cancels to 0. All right, copper CO3. What is CO3? That looks like a polyatomic. That is carbonate, copper carbonate. Cu, what kind of cation is this? This is a transition metal. I think these are the hardest to do because we actually don't know what the charge on copper is until we figure out the total amount of negative charge we have from our anions. So we just have one carbonate here. How do I know that? We don't have parentheses around it with another subscript or anything. We just have one carbonate, and it is a -2 charge. So the total amount of positive and negative charge here is -2. So that means the total amount of positive charge on that one copper cation is +2. Okay, because those have to add up to 0. So we need to indicate that when we write the name. It's not just copper carbonate, it's transition metal. So we have to write copper 2 carbonate. Okay, questions there? Any questions? All right, I think I have one more question on number 3, then we'll jump into chapter 4, and we'll be pressed for time to finish chapter 4 because there's a lot, but let's look at this problem and then we'll do chapter 4. I'm going to turn this. Tell whether each statement about ions is true or false. If false, why? Okay, number 1, a cation is formed by the addition of one or more electrons to an atom. What do y'all think? A cation is formed by the addition of one or more electrons to an atom. How do we get cations? Do they gain electrons or give away electrons? Okay, Hannah says thumbs down. You're right. So cations, we said, if we scroll up, they give away, okay? They give away electrons. So the addition, that's wrong. That's if we're forming anions. So this is false because cations do not gain electrons. We don't add electrons to form cations. Okay, number 2, group 4A. What does that mean? 4A, so just to jog your memory, we indicate, oh, I hate how blurry this is. We indicate main group versus a non-main group element with A's and B's. I don't know if you can see this. There's an A right here, and then this is a B. These are all B's. So these are denoting main groups, okay? If you go back over here, there's A's. Or it just says, anyways. So if it says 4A, we're talking about a main group. So we're talking about this group right here, carbon, silicon, germanium, that group. So group 4A elements tend to lose, they have 4 valence electrons. Do they tend to lose 4 electrons to yield +4 ions? True or false? What do you think? The one thing about group 4, we actually don't see them a lot in ionic compounds. They are all over covalently bonded compounds. But gaining 4 or losing 4, there's not a shortcut either way. And they don't like to give or trade that many electrons anyways. Okay, you can have up to like a -3. And I'm not saying carbon can never be an ion, but you don't commonly see it. So this one is going to be false because they don't participate in ionic compounds. All right, they are in covalently bonded compounds. They like to share their electrons because it's a lot of work to give away or receive 4. Okay, elements that form, number 3, elements that form anions are typically found on the left side of the periodic table. So let's go back over here. So where are the elements that tend to form anions? That's going to be like nitrogen, oxygen, sulfur, fluorine, chlorine, bromine, iodine. And that is over here on this side of the periodic table, okay? And that is not the left side, that is the right side. So this is false. Come on. This is false as well. Anions are typically found on the right side of the periodic table. All right. That's the end of chapter 3, moving on to chapter 4. We are now talking about covalent bonds. So, what is a covalent bond? It is a bond formed from sharing electrons. And all of this is still built off of the octet rule. We're still trying to achieve a full octet here. Remember we had the phrase, every time you share one, you gain one. So we use that as a motto to help us predict how many electrons an element or an atom would share. We also have this statement right here, the number of valence electrons needed to gain an octet, to get an octet, equals the number of bonds formed in covalent molecules. So a good example here is nitrogen. Nitrogen, swoop over to the periodic table. Where's nitrogen? Right here. Nitrogen is in main group 5. So what does that mean? That means it has 5 valence electrons. So how many does it need to get 8? So it needs 3, and that equals the number of bonds. It'll form 3 bonds in a covalently bonded molecule. And you would commonly see me draw this out all the time with, like, for example, ammonia, NH3. Nitrogen is classically involved in 3 bonds. Now it can look different ways. It could be a triple bond, okay, to another nitrogen, or it could be 3 single bonds or a double bond and a single bond, but 3 bonds. And that's how we figure these out. Okay, Lewis structures and condensed structures. We're just going to focus on Lewis structures, but we did a whole lab with condensed structures as well on Mastering Chemistry. So make sure you feel okay with condensed structures. I'm going to remind you of the rules for Lewis structures, and then we're going to look at molecular geometry. I'm going to try to briefly hit how we name binary compounds and polarity, and we'll see if we get all that done today. All right, the rules for Lewis structures. Find the total number of valence electrons for all the atoms in the molecule or the ion. That's the first thing you do. Then you can use that to check to make sure that you have everything accounted for when you finish drawing your structure. Then, number 2, start drawing lines between each pair of connected atoms. That represents 2 electrons in a covalent bond. So every time you have, an atom bonded to another atom, this is 2 electrons. So you count it 2, 4, 6, 8, 10, so on and so forth. Use the remaining electrons and add lone pairs so that each atom connected to the central atom, except hydrogen, gets an octet. We never put lone pairs on a hydrogen. So for example, if I had CCl4, okay, so I've connected all my atoms. What rule 3 is saying now, go ahead and start putting lone pairs on all the perimeter atoms. The chlorines are connected to the central atom until everybody gets an octet. Okay, so now these chlorines all have an octet once they get 3 lone pairs. All right. 4, place any remaining electrons in lone pairs on the central atom. That's where, like nitrogen, okay, ammonia, you would go back and you would put a lone pair on nitrogen in the end. What happened to my slides? Anyways, 5, if the central atom does not yet have an octet after all the electrons have been assigned, take a lone pair from a neighboring atom and form a multiple bond to the central atom. I think this part is the hardest, but I'll give you a classic example of where this occurs. Figuring out when multiple bonds is in a Lewis structure is not the easiest. So for example, carbon dioxide, CO2, carbon has 4 valence, each oxygen has 6, so total you should have 16 valence electrons in this structure. You're going to connect your perimeter atoms. Now we have all the atoms represented. Rule 3 says go ahead and start putting lone pairs on everything until everybody gets an octet. But when you're done, we have 16 electrons represented here. But what's wrong with this? Carbon doesn't have an octet. So if the central atom does not yet have an octet, carbon does not. It says pull a lone pair from a neighboring atom. So we're going to take off a lone pair from each of these oxygens and bond it to carbon until carbon gets an octet. Now remember, each of these little lines right here represents 2 electrons. So that's 2, 4, 6, 8. Now carbon has an octet. And remember, both atoms in the bond, so here, and I'm just drawing a portion of carbon dioxide, both carbon and oxygen claim all of these shared electrons. So we count them for both elements when we're counting octets. All right, that's the rules. Now let's do an example. Number 2. Let's just draw the Lewis structure for this one to remind ourselves how to do it. C2H5FO. Let's add up the total valence. So we've got 2 carbons. So from carbon 2 of them, each one has 4 valence. So that's 8 from carbon. Hydrogen, got 5 hydrogens, each one has 1 valence. Fluorine, we've got 1 fluorine, that fluorine has 7 valence electrons. Oxygen, we've got 1 oxygen, it has 6 valence. Total, you should have 26 valence electrons in this structure. Okay, now if you try to draw this out, you should remember that carbons and oxygens, any atom that can have more than 1 bond, so anything that's not hydrogen and is not a halogen could be a central atom. So you're going to connect those. I'm going to just go ahead and connect these. Okay, now we'll just start putting all the hydrogens on. We know carbon should have 4 bonds. So that's 5 hydrogens. So that's all my hydrogens and all my carbons. And I still need to have a fluorine in this molecule somewhere. I'm going to put it on the other side of oxygen because oxygen always needs to have 2 bonds and 2 lone pairs. And then if you count all of that, you should have 26 valence electrons in your structure. If you don't, you might be off somewhere and need to go back and recheck. Try again. All right, so that's an example with Lewis structures. Now let's talk about geometry. And we use the VSEPR model to do this.
Is there supposed to be lone pairs on fluorine or no?
Oh, thank you.
You're welcome.
Forgot those. If I counted, I would not have had 26. Now I will. Yeah. Halogens always get 3 lone pairs. Okay, VSEPR. It stands for valence shell electron pair repulsion. Okay. Because electrons create repulsion, that forces the atoms to be in certain positions next to each other, and that's what creates the 3-dimensional structures. Because if you're looking at this looks 2-dimensional, but it's not. It's 3-dimensional, and so this helps you remember everything's 3-dimensional. So how do we do this? Here's the rules for naming geometry. 1, draw the Lewis structure. We just did a review on that. Find the atom that you want to name. Okay, find the atom whose geometry you're interested in. It's usually the central atom. You will never name geometry for any perimeter atoms. I mean hydrogens and halogens. They have to be central atoms. Then find the number of, remember this term, charge clouds on the central atom. What is a charge cloud? It can be a bond, and the confusing part here is that we count in charge cloud world, a single bond, a double bond, and a triple bond are all just 1 charge cloud. So even though a triple bond has 3 bonds in it, it's still 1 charge cloud. Okay, just like a single bond is 1 charge cloud. So you'll count the charge clouds. Bonds or lone pairs can also, they count as 1 charge cloud. Then you use this table and you predict the shape. Okay, remember I edited this first column. I said number of bonded atoms. So look at the number of bonded atoms, the number of lone pairs, the total number of charge clouds, and see how that adds up to get your geometry name. Okay, so you'll have this on your resources page. Let's actually do an example down here. Well, what do you know? This molecule is the same as above. Let's just do that one for time's sake. So we already have the Lewis structure drawn out. So let's say I want to name oxygen here. First thing we need to do is figure out how many charge clouds are on oxygen. What do y'all think? Remember, bonds and lone pairs count as charge clouds. So total, yep, we have 4 charge clouds, okay? 1 bond, 2 bonds, 1 lone pair, that's 3. That's 4 charge clouds. Now let's go down to the table. So we are down here in this bracket where it says 4. That oxygen is bonded to a carbon and it's bonded to a fluorine. So we've got 2 bonded atoms and it had 2 lone pairs on it. We got 2 lone pairs, so we call it bent. Okay, what if we were trying to name this carbon right here? How many charge clouds on that carbon? No guesses?
4.
Oh, yes, thank you. 4. So we're down here again, but this time we've got 4 bonded atoms. No lone pairs. Carbon should never have lone pairs, so it's tetrahedral. All right. So there's an example with geometry. You could also name this carbon right here. It would also be tetrahedral. Any questions on this? Is this jogging your memory? Okay. Remember how to do some of this stuff? Okay, good. Let's go back up and see if my slide reappeared. Okay, here it is. Now we're going to briefly go over naming binary covalent compounds. What does binary mean? Binary means there's two elements. So if you look at all these examples, this is problem 4.81 from the textbook. There's just two elements here. Here's the method you use. You do the prefix of the first element, then you name it. Then you do the prefix on the second element, then you name the element. And I forgot to say this, but the end of element two should be IDE, just the way you name anions. So you'll change the ending of that second element to IDE. Now remember, what are your prefixes? Mono, di, tri is 3, tetra is 4, penta was 5, hexa was 6, hepta was 7, octa 8, nona was 9, and deca was 10. So, for example, and another thing here, you most all the time omit the word mono for the first element. There's certain cases where you do use it, but I'm not gonna pull straws and split hairs and test you on when you do and don't use mono. So just pretty much know you're gonna omit mono for the first element if there's only one. For example, we only have one phosphorus here. We're gonna omit mono. We're just gonna write phosphorus. We have 3 iodines, so it will be tri. Iodide. Ending is IDE. Phosphorus triiodide. So we're not going to write monophosphorus. We're going to omit that. Oh, let's do C and E as well. So go ahead and attempt those. Okay, for this one, you should have tetra, phosphorus, trisulfide, and for E, you should have dinitrogen, pentaoxide. Actually, we don't put 2 vowels together. So we're going to just say pentoxide. But this will likely be a multiple choice question, and you wouldn't have to write it out for me anyways. So the option should be spelled correctly for you. Okay, questions on that? We're almost done. We've got like 4 minutes. Do you think I can squeeze bonding into the next 4 minutes? Polarity, I mean, polar bonds and polar molecules. Let's see if we can. I'd really like to finish chapter 4 because then we get to chapter 5. I'll pick up with chapter 5 tomorrow. Okay, real quick. Polarity all has to do with difference in electronegativity. You guys remember this chart? We've used it like half the semester. So you look at what elements are in your bond, you go find their electronegativities, the values on this chart, and you take the highest minus the lowest and you look at the difference. And then you classify it as nonpolar, polar, or ionic based on, I'll give you that little table too. If it's greater than 0.5, it's polar. If it's less than 0.5, it's nonpolar. All right. So here's a good problem. Arrange the following molecules in order of increasing polarity. We're going to start with the least polar, the smallest electronegativity difference, and we're going to order them to the most polar. So HCl, so we need to find hydrogen and chlorine. Hydrogen has a value of 2.1, chlorine is 3.0. So we'll do the highest minus the lowest, 3.0 minus 2.1, and we get a difference of 0.9. So we'll hang on to that. We'll come back to that in a second. pH3. If you look at this molecule, we've got 3 bonds, sure, but they're all identical. So we're really just examining a phosphorus hydrogen bond. So again, hydrogen's 2.1, phosphorus is also 2.1. So the difference there is 0. 2.1 minus 2.1. C is water. So we have 2 identical bonds here. It's just an oxygen-hydrogen bond. Oxygen is 3.5. Hydrogen, again, is 2.1. So the difference is 1.4. And then D, we have carbon with 4 fluorines. For time's sake, I'm not going to draw in all the lone pairs. So we're just looking at a carbon-phosphorus bond. Carbon is 2.5, fluorine is 4.0. So 4.0 minus 2.5 is a difference of 1.5. So now it says order them in increasing polarity. Start with the least polar, order them to the most polar. So what you should have, A is the least polar, HCl. So it should be A. Oh, wait, sorry, B. B is 0. B and then A, and then C and then D. Okay? So that's how you do that problem. So that's a good little review on bond polarity. For molecules, in my remaining 1 minute, let me remind you, you're considering 3 things here if you're trying to determine if a molecule is polar or not. Number 1, does it have any polar bonds in it? If it's all carbon and hydrogen, it will have no polar bonds. But if it does, then it could be a polar molecule. 2, does it have any lone pairs? Okay, if it has lone pairs, then the electron density is going to be where the lone pairs are, and you can draw a dipole in. 3, the shape. You're looking for symmetry. If there is symmetry and the dipoles cancel because they're pointing opposite directions, then your molecule will be nonpolar overall. Okay, so for example, CCl with 3 hydrogens, CH3Cl. We know carbon-hydrogen bonds are never polar, but this carbon-chlorine bond is polar. So you're going to draw the dipole in, pointing towards the element that is more electronegative, higher electronegativity, and you'll cross the arrow, making a little plus sign, because why? You have a separation of charge here. The carbon is a partial positive, the chlorine is a partial negative. And that's how you go about determining polar molecules with dipoles. Okay, that's the end of chapter 4. I'm going to stop sharing my screen. I can go back if you need me to in a minute. But if anybody has any questions, you want to hang around and ask me anything, it can even be regarding stuff not on our review. I'm happy to answer those. If not, listen, I've really enjoyed having all of you in the course. I wish I could have gotten to know you all more in person, but I wish you all the best moving forward. Thanks for being great students, and I hope you all have a wonderful Christmas break.